All right, our last section of new material in Intermediate Algebra 211, Cartesian Coordinate System, Day 2. The first question is going to look like something we've already done before, finding x and y intercepts and graphing. But I wanted to make sure that we were all remembering what we did last time to move on to what comes next in the material. So our x and y intercepts, of course, we talked about before. Our x-intercept is when y is equal to 0. So we're going to take 2x and we'll replace y with 0. That will end up giving us 2x equals 4. If we divide by 2, x is equal to 2. And of course, looking at the homework and things from last time, you remember that that is the ordered pair to 0. Okay, nothing new on that problem. We're going to find the y-intercept, same way as before, where x is equal to 0. So we have 2 times 0 minus y equals 4. Of course, this piece is equal to 0. So negative y is equal to 4. Either multiply or divide by a negative 1. And you find that y is equal to negative 4. Sorry, I'm kind of out of space there. And that corresponds to the ordered pair 0, negative 4. Okay, so that's just like we did last time, nothing new. We are going to combine that with the idea. It says then use them to graph the line. And you don't have a graph right there, but we're going to put them on my graph, and you're going to create your own. So we have the ordered pair 2, 0. So that would be right here. And then the ordered pair 0, negative 4. Approximately right there, and connect them with the arrows on the end. Okay, and also going the other direction, we're going to do a graph, but it's not drawn in your book yet, and I'm going to flip over the screen to what the graph is here, and I'm going to actually draw it for you. I couldn't get the graph to get in there the way I wanted it to. So this is the graph you're going to draw. And try and draw it carefully. So I'm hoping the first thing you notice is it's not a line. Correct? This is the graph. Looks like a V, upside down V shape.
What's the top of it?
The top of it is actually at a height of 3.
And negative 2?
Yeah. So when you're looking at them, that's kind of the important feature. So you're identifying the right pieces, Kenny, of what you're looking for. This is actually at a x value of negative 2, and it's at a height of 3. Okay? That's an important feature. There's a couple other important features as you're trying to draw it in, and that's hopefully the important features of where it's crossing the axes that you see it happening at, right? And in fact, that's what the question's asking us here as well. We didn't graph it. It's given to you. I just didn't have it say. I couldn't get the image to import like it should be from where I found it.
Okay,
Sometimes my images come in really nicely, and sometimes the places where I find them from, they don't import nicely into PowerPoint or into your notes with Word or whatever. So that's why. So you would be given the picture to start with. Okay, picture's already there. And it was kind of like the ones you had this last homework assignment, right? Some of them already had pictures in there, and you were asked to identify some features. Same thing. So this asks us to find all x and y intercepts. So we need to find x-intercepts and y-intercepts. All right, so what are the x-intercepts that you see? Yep, 0, 0, and negative 4, 0. Okay, remember it's the x value that comes first, so negative 4, 0. And what's your y-intercept? Yeah, it's actually the same as one of our x-intercepts. It's also 0, 0. Sometimes that happens, sometimes it doesn't. Make sure you're identifying both. So the fact is that you're going to label x-intercepts in these two, y-intercepts in it's this one, even if they duplicate, okay? So what we're going to see happen in this section of material is that some of our graphs, and in particular most of our graphs, are no longer lines, all right? We're going to be finding the same features that we found before, x-intercepts, y-intercepts. They just aren't going to be of lines. So this is a graph of one that's not a line. You might actually have recognized what this graph is. If you didn't, don't stress about it. We'll talk about it in college algebra, but this is a graph of an absolute value. That's how you get the V shape. But we aren't going to stress about that right now. You're going to see we have a couple other equations coming up that are not lines either. In particular, the red flag on number 3 that makes it not a line is that power 2. Lines don't have squares. And on number 4, you have variables in a denominator. That's not a line either, okay? But we're asked simply the same question we were before. Find the x and the y intercepts. But the process starts out very similarly. An x-intercept is when y is equal to 0. And a y-intercept is when x is equal to 0. Okay, so it's the same starting spot we were before, no matter what the equation is. So on the first one, if x is equal to 0, then I have y squared plus 0 minus 16 equals 0. Did I do it backwards? I did it again. How did I do that before? That's the one over here. We'll do that one then over here. Sorry about that. I don't know why it keeps flipping around today in my mind. Okay, let's try it again then. Y is 0. Okay, so y squared plus x minus 16 equals 0. Is that better? Yeah, it is. Okay. So clearly this is 0. And my goal is to solve for x, which should mean I need to move the 16. So I'll add my 16 to the other side. So this is going to be x is equal to 16. So my x-intercept, I don't have space to write it there, so I'll write it over here to the side, is 16 for x and 0 for y. That's my x-intercept. X is 16, y is 0. On the other one, I still get a 0 here in the middle when I was starting to do it wrong before, sorry. But I still have now a squared in the problem, and I haven't had that happen before because I was doing lines before and now I'm not. So this is y squared minus 16 equals 0. So what do you suppose you would do first? Because we haven't solved equations like this. Yep, we're going to add 16. So that's going to leave me with y squared on the left and 16 on the right. And then what? We're going to take a square root. And what's the square root of 16? 4. Almost.
So then y is 0.
We're missing something still. Somebody said it. Say it louder, Cooper. Plus or minus. So we mentioned way back in section 10, your favorite section that keeps coming back up, that when radicals are given in a problem to start with, it's asking you for the principal square root. You don't have to worry about pluses and minuses. But when you put a square root into a problem, you automatically put a plus or a minus whether you realized it or not. And the reason is because there are two numbers that I can square and get 16. 4 squared is 16, and negative 4. Negative 4 squared is also 16, right? So there are two answers. Y is 4 and y is negative 4. So my y-intercepts are actually 0 for x and 4, and 0 for x and negative 4. I have two y-intercepts. Okay, I don't want to jump the gun. We'll talk about some graphing on these in just a second, but we'll just pause there for the moment, okay? All right. The other one here was the rational one here at the bottom. This is called a rational equation. We'll talk more about those also in college algebra and in a little bit more here too in a minute. But for starters on this, we're just asked to find x and y intercept, just like we were on the previous problem. So we'll see if I can get it right this time. Your x-intercept and your y-intercept. Your x-intercept is when y is equal to 0. That's the harder of the two here. And your y-intercept is when x is equal to 0. Okay. So if y is equal to 0, it means I have 0 on the left-hand side of my equation. I have 1 minus x squared on top and 5 plus x squared on bottom. So far, so good? Okay, do you guys remember when we've done with some of the different things with fractions, solving with fractions, we did things called cross-multiplying? Yeah, do you remember that? Cross-multiplying here is very friendly. The 0 on the left-hand side is the same as having 0 over 1. Are you with me? So the cool thing is, if I cross-multiply here, what's going to happen on one of those diagonals? Yeah, one of them is going to be 0, right? If I multiply 0 on the top left diagonal to the bottom right, I'm going to get 0. So this diagonal right here is nothing. I get 0. The other diagonal is actually also kind of friendly because I'm multiplying by 1. So when I multiply this diagonal, it's just going to be the numerator on the other side. It's going to be 1 minus x squared. So good? Okay, so we're going to clean this up, so shifting some things around and so forth. I'll move my x squared this time. So I have x squared equals 1. It's kind of ended like the last problem, so what will I do next? Take square root. So x is equal to what? Plus or minus 1. So I have two x-intercepts. I have 1, 0, and I have -1, 0. So in the last problem, I had 1 x-intercept, 2 y-intercepts. This time I have 2 x-intercepts. Let's see what happens for y. So my y-intercept, where I let x equal 0, means I have y equals 1 minus 0 squared over 5 plus 0 squared. This is the cleaner of the two here, right? These 0 squareds are 0. So what is my y-intercept?
1 over 5.
Yeah, 1 over 5. So as an ordered pair, that's 0 and 1/5. Okay? So the algebra for solving is not insane. It's not crazy. But there's more involved than solving for lines. Agreed? There is. There's more involved than when we had for solving lines. So graphing non-lines. When a graph is not a line, it requires more points to graph it. How many points did we need for a line? 2. 2 is really all we needed. Absolutely. Here, we need more than 2. 2 will not be enough. Okay? We want to try to choose well with at least 5 points. Not 2, 5. And this sort of phrase, choose well, is really vague. I know. But I think that once you start doing it, you'll figure out what that means. And I'll try to help you do that. So a lot of times, the numbers -2, -1, 0, 1, and 2 are good choices. Not always, but a lot of times. They're a good default anyway. Okay? So we're going to try 4 different types of non-lines to graph. Okay, did everybody get all their blanks filled in on this one? Okay, good. All right, so here's our first one. Mentioned this one before, absolute values. We will talk more about all of these kinds of graphs, all 4 of them, inside of college algebra. We'll go a lot further in depth. We're just touching the surface right now for intermediate algebra, looking a little bit at graphing. So our equation is y equals 3 absolute value of x. So we're going to make an ordered pair chart, x and y, and we're going to pick some nice values. And I'd like to show you those values I mentioned before as being nice values here. So why are they nice values? Well, one of the reasons that they're nice values is because I've got an absolute value and I'm picking some positive and some negative. That makes sense, right? 0 is often a nice value to pick. It's often easy to solve with. And this one actually ends up giving me some very symmetric kinds of images too. So we're going to start with the -2. If I put -2 in for x, what's the absolute value of -2? 2 times the 3 that's in front, 6. This is positive 6.
Wait, how was that? Oh, because it's absolute value.
Yep, those absolute values, you're right. How about -1? What's the absolute value of -1? 1 times the 3 in front gives me 3. All right, what's the absolute value of 0? 0. And 3 times 0 is 0. Zeros are often nice numbers to pick. How about the absolute value of 1? 1 times the 3 in front, 3. The absolute value of 2, 2 times the 3 in front, 6. So notice the pattern here. I went 6, 3, 0, 3, 6, right? There's a pattern that comes about because there's symmetry involved in these particular choices. So over here on my graph, I've got -2, 6, that's here. I've got -1, 3, that's here. I've got 0, 0. I've got 1, 3, and I've got 2, 6. Okay, so all absolute values are V-shaped, okay? You can kind of see why it has to be the case on this one, because if you looked at just half of this graph, you actually see a line, right? The slope is the same. You go down 3 over 1, down 3 over 1. Do you see that? Over here you go over 1, up 3, over 1, up 3, or up 3, over 1, or whatever, okay? So this is actually the joining of two different lines. The other thing that's actually interesting, and I'm going to draw it, don't draw this part that I'm going to show you real quick because I'm going to quickly erase it, but if I were to look at just the left hand or the right hand side here, this line, what absolute values do is they take everything that was negative and they flip it up. So if I were to take that part that just circled in green and I were to flip it up, you'd see that I'd get the other side of this V. That's what's actually happening from a graphical standpoint here. So what I want you to remember from all that is that there are reasons behind why the absolute value is doing what it's doing. It is, in fact, creating a V-shaped graph. So if you want to sort of kind of make yourself a note that always absolute values are V-shaped, that's a true statement. So when I connect these now, I'm going to get this piece, I'm going to get this piece, and I should have arrows on the ends pointing up. It's a V graph. Okay? Always going to be for absolute values. Any questions on the absolute value graph before I shift to a different type? Okay. Next one we're going to look at is y equals -x squared. So again, we create our ordered pair chart. And again, there's going to be some symmetry here. Values that I pick are going to have common output values. We're going to get some patterns going on. We're going to choose those same -2, -1, 0, 1, and 2 ordered pair x values and see what happens. So if x is -2, right here, and then I square it, right, square it. So -2 squared is 4. It's positive 4, right? -2 times -2, positive 4. And then I have the negative in front making it a -4. So the first one is -4. Now I take -1 and I square it. So what's -1 squared? 1. And then I have a negative in front of it, right? Yeah, so that's...
Negative in front of the x, is that what you're talking about?
Yes. So I'm what I'm doing is I'm working from the inside out.
Okay.
And so the equations are not terribly messy at this point. So I'm not writing them down. If it bothers you that I'm doing that and you want to write them down, you totally could.
No.
Like
I
that.
was confused on when you were saying that.
Yeah.
I get it.
Okay, so we're negative 1 squared is going to be 1, and then the negative that's in front of that would make it a negative 1. 0, he's our friend. 0 squared is 0, and then the negative or the opposite of 0 is still 0. Positives are friendlier to sort of think about. 1 squared is 1, and then the negative in front makes it a negative 1. 2 squared is 4, and the negative in front makes it a negative 4. And again, you see pattern, right? Negative 4, negative 1, 0, negative 1, negative 4. It almost feels like, well, didn't the pattern kind of just do the same thing that the absolute value did? So let's graph it and explore that idea just a little bit. So I have negative 2, negative 4. I have negative 1, negative 1. 0, 0, 1, negative 1, and 2, negative 4. Okay, so you might be tempted to look at this and say, well, it looks a lot like the last one, especially because it's kind of on a small scale. It's a very small scale in my graph to be able to see it. The problem is that they're not forming lines on each side. So if we look at the left-hand side over here, and I'll just start with my bottom point here, where I've got negative 2, negative 4 plotted. I would actually go up 3 and over 1 to get to my next point, but then I'd go up 1 over 1. The slope's not the same, right? It's steeper at the beginning. It's a hill, right? It's a hill. It's not, it's not a roof. It's a hill. And so it's steep at the beginning, and then it becomes more gradual as I continue. It's not a V-shaped. Do you remember what the shape is? It's a U shape. It's a parabola, and it looks something like that if you're connecting them. So again, what I want you to remember is that absolute values create V shapes. Squaring, quadratics is what it really is, create U shapes or parabolas. Okay, so we get parabolas out of this particular image.
And we got the U shape because it's x squared.
We got the U shape because x is squared, exactly. So when we look at number 7 and we see that x is squared, our expectation should be that what shape are we going to get for number 7? A U shape. Now, it's going to not be in the same place because it's a different equation, but it's going to be a U shape. So in particular, let's take a look at number 7 with that particular equation given. So x and y. I can still use that negative 2, negative 1, 0, 1, and 2 that are there. Now, I actually had all the values from this first part because this is the same equation at the beginning, isn't it? All right, it's the same thing. It's negative x squared. So if you kind of refer back to your table, we can shortcut this one a little bit. We already calculated each of those. We just need to add 5. So on the first one, I had negative 4, and if I add 5, what do I get? Yeah, I get positive 1. I had negative 1, and if I add 5, I get 4. I had 0, and if I add 5, I get 5. Had negative 1, and if I add 5, I get 4. And then I had negative 4, and if I add 5, I get 1. Still a pattern, right? 1, 4, 5, 4, 1. Do you guys ever do patterns like that when you do like your phone codes and stuff? Easy to remember? Probably. Something that's easy for you to remember and some kind of a pattern. So this would be a really nice pattern. We can actually plot these points next, just like we did on the earlier problem. Negative 2, 1. Negative 1, 4. 0, 5. 1, 4. And 2, negative 1. I'm sorry, 2, 1. I said it wrong. I plotted it right. 2, 1. It's another U. In fact, it looks a lot like the first U, right? The shape's the same. How does it compare from the graph?
Just moved up a bit.
Just moved up a bit. In particular, how much of a bit? 5. And that should kind of make sense based on the equation, right? Yeah, and we'll explore a lot more of that in college algebra. But we can take a look at that. Yep, we'll get there.
Ah, the memories.
Oh, the memories. Okay. You ready to take a look at number 8?
No. Yeah.
Or you just not want to look at it, Jasmine, because there's fractions? That's what I thought. Okay, we're going to look at it anyway. All right, so if you really want to keep using the -2, -1, 0, 1, and 2, you can. The problem with that one on here is that it's going to end up giving us some values that are fractions instead of that aren't fractions. And so it's kind of messy. So I'm going to suggest that we start with the -2 and see what happens, because it's going to be a pretty nice value, and then just try to pick some values from there. So my values are not necessarily going to go in order on my chart, because I really want to pick 5 values, but I kind of want them to be nice values. Now, 0 is always, well, it's not always nice, but it's really nice here. If this is 0, and I do 0 cubed, what do I get? 0. And then 3/4 times 0 gives me 0. So 0, 0 is still a nice value. 1 is not especially nice. I mean, it's not like the worst thing ever, but it leaves me with fractions, and fractions are kind of hard to graph accurately. Don't you agree? I think they are. So I don't really want to pick a number 1. We can pick that in a second. Let's pick our 2 first, because 2 actually works out pretty nicely. And if 2 is going to work, then -2 will as well, just so you know. So if 2 is what we've chosen, what's 2 cubed? 8, okay? So 2 cubed is 8. So now I have 3/4 times 8. Yeah, the 8 and the 4 will reduce. 3 times 2 is 6. Yeah. I got a whole number. Whole numbers are nice. But let's do -2. So what is -2 cubed? -8. So when my 8 and my 4 cancel, I'm left with a -2, which then gives me a -6. Yeah. Okay. So 2s and 0s were nice. 1 was not. Yes, Damaris.
How many do you require us to do? 5?
You need 5. Yeah. So we've got 3 of them. And if we can find one more, and we do use this idea of symmetry, we probably can get the other one. So I think 4 was a good choice by Kaylee. So let's try a 4 and see what happens. Now the number is going to be kind of big, so graphing it might look kind of funky. We'll see what happens. I think it's going to be kind of big.
Big numbers just like
All right. So what is 4 cubed? It is 64. So you might not like it. Try it.
Isn't 4 times 12 64?
No. 4 times
Why am I
16.
math?
Because you are required to have it. All right. 4 and 64 will cancel, though, and they'll give you 16. 3 times 16 is,
Gross.
what is it? 48. Okay, so 4 and 48,
Can we omit an option?
we'd actually have -4 and -48. So keeping out the fractions actually ends up giving a really big number here that might not be preferable. Let's go back and do 1 and -1 because I think it'll fit on our chart better. The numbers here just got really big to make that happen. If I do a 1, I get 1 cubed, which is 1. And then 1 times my 3/4 would be 3/4. I mean, it's not great, but at least it's on the chart, right? And then what's going to happen for -1? That one's going to be -3/4.
You know how I just do, whenever I get big numbers like that, I do that thing where I just make it go off the graph by like 1 point.
Oh, okay. There you go.
I do that.
All right, let's plot this one. I have 0, 0 in here. I have 1 and 3/4. Well, actually, we'll just go down the chart. We have 2, 6. So 2 6s here. And I have -2, -6. That's here. So that's different. We haven't had that happen imagery-wise yet. I have 1 3/4. So it's kind of in between, 0 and 1 on the height. And I have -1, -3/4. It's right here.
And how did you go on 1 and 3/4?
I plotted it between 0 and 1.
Okay.
Yeah, there's the accuracy is definitely not there, no doubt.
Oh, I love these little
But roughly
tiny curvy
speaking,
lines.
it's, in the right area, kind of. Yeah, so these are the ones that look kind of like a spaghetti noodle. I like that. We're going to go with spaghetti noodles, except I'm hungry, so I'm not really sure that was a good choice.
I love spaghetti.
That was bad. Let's try it again.
I love Italian.
I was gonna say,
All right, something like this. Okay, that's not great, but generally speaking, it's the right shape.
it's not good, but it's not bad.
It's not good, but it's not bad.
Spaghetti low-key gives me trauma.
Okay, so you've noticed as we've been through, I've kept using this word symmetry, right, when we've picked values. That's the other component we're going to actually take a look at as we end this section, is symmetry. There are 3 types of symmetry possible within a graph. And it's not an either or thing. You could have 1 or you could have 2, you could have none, right? It's any possibility kind of a thing. X-axis symmetry is a graph that's a reflection of itself over the x-axis. Y-axis symmetry is a graph that's a reflection over itself on the y-axis. And origin symmetry is a rotation around the origin. So it's almost like a spinner in a board game, right? Like the game of life. You spin it, and it spins itself around the origin. And it's a rotation of 180 degrees. I don't have that written down, but that's probably valuable information. Okay? So like my son, he put his mask on upside down today, and my daughter was like, that's upside down. And he rotated it 180 degrees, and now it's right side up, right? There's your real life example. There you go.
Oh, yay.
Yeah, okay.
Does this say
So, which one? It says of. That's a cursive F. It's just weird. Yeah.
Oh, I thought it was an O and a really.
It looked like it's
I was
this
like,
side, and then I was like,
Sorry, that's my fancy F. Not my fancy F, my cursive F. OF of 180 degrees. Now, I mentioned this, but we've actually got a place for you to fill it in, I guess. Oh, where's my, I don't have any screens. Wasn't that fun? Okay, well, we'll just write it by hand then.
Oh.
It's not here, so sad. I can do this, though. Watch this. Look, there's a blue backdrop. It's not the same blue, but we'll pretend. All right, so note. It says note. Can you see that black on the blue? Good. All right, a graph can have one of these,
This.
two, oh, sorry, these, two of these. See- Uh-huh, you're exactly right, Jasmine. Or none of these.
I thought it was
Yeah.
Low-key kind of like this better than these.
but not.
Let's not can have one of this.
Actually, there's a typo. It shouldn't say two. This one should say three. Or all. That's my typo. There we go. I was like, I wasn't looking at my notes. Sorry. You can have one, you can have all of them, or you can have none of them.
Why can't they have 2?
Okay, so we're going to go back and we're going to look at the 3 that we did before, or 4 that we did before, and we're going to identify which they have. And then I'm going to actually fill in the gap for the ones that I didn't actually have show up in mine, because I told you you could have one, all, or none. So let's look at the graphs that we had here. Number 5. All right, x-axis, y-axis, origin.
X-axis. All three.
What you want to do is you want to think about putting in a dividing line somewhere. Is there a place where you could put in a dividing line and fold it and have a mirror image? Yes, there is. Where would that fold be? The y-axis, so it is a y-axis symmetry. Yes. Okay, so on number 5 on your paper, it's not listed on mine because I don't have my screen showing up, but this actually has y-axis symmetry. Notice, It doesn't have x-axis symmetry, right? Along the x-axis, there is no fold down and it looks the same. You don't have that. How about my second graph?
Definitely Y.
Definitely y. So this is your number 6. Also a y-axis
And I feel like-
symmetry.
Could it be? I don't know. Because like if you cut it like that way.
If you folded it along the x-axis or cut it along the x-axis and you flipped it, would it land on itself?
It has to be across
No.
the like.
Right.
Okay.
Yeah, it wouldn't work. How about number 7?
Why?
Yeah, another one y-axis. Y-axis occurs more than any of the others. Hopefully you're seeing that. So far, it's the only one we've seen happen at all, right?
That's definitely no. The last one's definitely.
No.
No.
It's X. No, it's the X.
Wait, because it.
No way.
Because if you hold it down,
This is more than I've heard Daniel talk all semester.
If you, I don't know. I'm just.
Okay, but if you
It's
like
both.
folded it
All-
hamburger style, then you could also like fold it hot dog style.
Ooh, so
It's a
so
rotation.
Bailey's thinking maybe we should fold it twice. And Damaris, what'd you say?
A rotation on the origin.
It is a rotation around the origin. This is a spinner. Okay, imagine, right? So I hope you haven't been in a car accident where this has happened, right? Where you've spun 180 degrees. But if you spin this 180, I have too. If you spin this 180 degrees, it will land right back down on itself, won't it? It will. This has origin symmetry.
So it's only origin symmetry?
Only origin.
That's dumb. I don't like this game.
I was where you were thinking. I was
Okay.
You fold it twice.
All right, so let me actually give you a couple pictures. Okay, guys, we're almost done. Let me give you a couple pictures so you can see what it does look like when you have x-axis symmetry or all of them, because we didn't have either of those show up, right? Okay, so if you had x-axis symmetry, you would actually have a graph that looks much like your y-axis symmetries. It would just be centered like this.
Oh.
Okay? Now, there's a reason that we don't see that happen very much. Does anybody remember? Because it's not something we've talked about this semester. We will talk about it in college algebra, like immediately. This graph is not a function. Okay? So if you know what I'm talking about, great. If you don't, you could just ignore what I just said. It's all good. But that's the reason, is that we're actually talk about things that are functions even before we call them that far sooner than we talk about things that aren't. Now, my all three. The all three graph.
Do you have to judge?
No, I don't like it.
It's
Then
just a
why-
circle.
Why is that one all three and not?
Because it's a circle.
Because if you fold it along the x-axis, it lands on itself. Open it back up. If you fold it along the y-axis, it lands on itself.
And you could give it a good old
And if you rotate it 180 degrees, it lands on itself. The difference between that and this graph over here is that you would actually have to fold it twice before it landed on itself, right? But I only need one. I should only have one fold if it actually fits the criterion.
So we're just looking for it to just be one.
Yes. Okay, it can only have one piece. So over here, it has x-axis symmetry, right?
Yeah.
Has y-axis symmetry, right?
Yeah.
And it has origin symmetry.
Yeah.
And there are plenty of other graphs I could have drawn for those two, but there are other options.
Okay, what is it?
No, that's not what I said. I said origin symmetry. Who said that?
I said
Max.
on the drawing.
That's what I thought you said.
Okay,
Yes.
so what does the none one look like?
What does none look like? Oh, I didn't draw that. You're sure?
Sorry,
Okay.
I just.
So none would be, it could be any of the kinds of graphs we have. They're just not centered. So like this would be a none graph.
Does it go
It has symmetry. It's just not x symmetry or y symmetry, right? So it does have symmetry. It just doesn't have the symmetries that we've described. Okay? All right. I feel like we've been in class for a really long time today. Yeah. So you guys good with quitting just a few minutes early? You still have to have it done before next class period, and we have a quiz next class period.
When I submitted it, I didn't want you to cut it right here.
Okay, sounds good. All right. Have a great evening, guys. I will see you tomorrow. We will do questions, homework questions and so forth, and we will take a quiz. That's our plan. So have a great evening.
It's over the last 3 things that we've done.
Yes, it's over everything since the last quiz that we had, which I believe is the last 3 sections of material we've done. Correct.
Yeah.